So, Vanakkam. So, we will continue our lecture on engineering seismology. So, we have been discussing about the seismic hazard analysis and the essential component of the hazard analysis. So, we have talked about the preparation of the seismotectonic map, okay, how you can prepare a seismotectonic map, how you can consider a different seismotectonic parameters in the region. So, followed by we also discussed about the seismic data collection, homogenization and declustering and completeness analysis. Okay. So, by doing this entire process, okay, so you will be knowing what are the seismic sources are active in the region, what are the seismic sources, what is the M minimum. M minimum means a minimum magnitude occurred in the region and complete period. Okay. So, the complete periods are essential to recurrence relation to develop by the Kustenberg-Richter relation, because that relation says that you should only develop a GR relation for the complete data, okay, not the incomplete data. But later Kitchko and Selwell, they also introduced a method for incomplete data, but we are only concentrating on the GR relation, that is the most widely used relation. Okay. So, the complete data period is, that is what it plays role. So, this data will indicate that what is the seismic city associated in the particular seismic steady area. Okay. So, for the future seismic hazard analysis, okay, you have to identify what is the maximum possible earthquake you need to consider, or maximum magnitude you need to consider for design of particular structure. Okay. So, that process, okay, the estimating of the maximum probable earthquake or maximum credible earthquake at any seismic steady area is actually process of estimating the maximum magnitude. Okay. So, today class we are going to talk about the maximum magnitude method estimation, and I also talk about the how the seismic steady area related with the your MMAX estimation. Okay. What are the different methods are there. Okay. So, how these methods will affect your data how will contribute to the MMAX value in the region, and I also developed a new methodology which is called as a regional rupture based approach to estimate MMAX. Okay, that methodology also I will discuss okay, in the today class. Okay. So, the MMAX, okay, basically the earthquake potential of the region, typically the MMAX, which can be estimated, okay, by knowing the rupture length in the particular region, okay, or rupture area in the particular region, and maximum surface displacement correlation in the particular area. So, these are all the some of the empirical formula one can use. If you know that this is my rupture length and rupture area based on the old seismotectonic details, then you can estimate what is the MMAX using the empirical correlation. So, this empirical correlation also we will discuss in detail. So, or you can estimate theoretically, okay, if you know the slip rate, as we have know that the slip rate, okay, associated with the seismic movement, the M is equal to shear modulus of the rock, area of rupture and the average displacement over a rupture area. A slip rate, area of the rupture and the rock properties, if you know, you will estimate M naught. If you estimate M naught, from the M naught you will get a your MW, that MW will be taken as a MMAX. Okay. So, theoretical based approach and empirical based approach, but it is very difficult to get a rock where the rupture is taking place. Okay. You will be knowing only the from old earthquake where the rupture was occurred. For the new earthquake, you do not know what depth is going to occur, even though you have some fair idea, but it may come more or less. Okay, you do not know. 20 meters is your average depth in the earthquake in the region. If you take 15 meter or 25 meter also it will occur. We do not know. So, that you cannot really accurately estimate. So, the theoretical based approach has a always constraint. So, because of that the empirical based approach are very widely used in the MMAX estimation. So, the MMAX is basically the maximum magnitude is an important variable of the seismic hazard estimation. It reflects a maximum potential strain released at large earthquakes. Okay. So, the instrumental and historical record of earthquake are often too short to reflect a full potential of the fault in the thrust. So, if you do not have the proper instrumentation, proper documentation in the historic times, you may not be knowing what was the MMAX, a potential fault rupture is happened in the region. So that you should always remember when you estimate a M max. So the maximum regional magnitude M max is defined as a upper limit of the magnitude given a region, a synonyms of the with magnitude of the largest credible earthquake. So beyond that you can't expect any earthquake. That is the maximum magnitude of the particular earthquake. In other words, it is a sharp cut-off magnitude at a maximum M max, so that by definition no earthquakes are to be expected with magnitude exceeding M max. Okay. So now you may understand how M max estimations are very important. Okay. So the estimation of maximum earthquake magnitude is essential for seismic hazard analysis, okay, for engineering, earthquake engineering community, disaster management agency and insurance industries to decide how much the seismic energy will be released, how the losses will be there, okay, how many people will die, how many collapse you can expect, all that. But as on 2017 or 13, I don't know, maybe 13. So up to that or 2011, Kitchko and Singh said that there is no universally accepted practice, okay, by estimating the value of M max. Even though it is very important, there is no universally accepted procedure to estimate a M max. Okay. So this issue was actually realized by my research team, myself, and we worked on the alternate M max estimation method, which can be adapted irrespective of the seismic steady area. Okay. That we are going to discuss part of the today class. So what are the method M max are estimated in the general. Okay. So generally people will take the M max as a maximum observed magnitude in the region, that is called as a method 1. Okay. That is a method 1. The observed magnitude has been taken as a maximum M max. Okay. So that is the one way you can do. So where you know that. But if you have the very short catalog, okay, so this will lead to a very low M max value for the future design. Okay. So then the another one is the M max observed and add some increment. So this increment, okay, so can be added, depends upon the interest of the person and then some kind of relation with the your other parameter. So the other one is extrapolation of the magnitude frequency graph. Okay. So where you generate a magnitude frequency graph, which we have seen, no, extrapolate that and take that. The other one is yes, fault rupture based method, like mark method. So what he says that if you know the length of the fault, you assume that the entire length of the fault, so much portion will be rupture. Then you know, if you know the rupture length, you can convert that into the your M naught or moment magnitude based on the empirical relation followed. Okay. So that is the mark method, which is called as a M4. So the strain energy method, so it is actually taking into account of how much earthquake occurred in the region, how much energy released. Okay. Then by cumulative that you can get a future earthquake, that is called as a strain energy method, the M5. The Kitchko and Singh method, M6, it is further divided into 12 method. So this method basically a statistical method which account your seismic data in the region. Okay. So it does not do anything, only statistically look at your data and try to arrive the M max by this one. So we are going to discuss all this method in detail plus the new method what I have developed. So the maximum magnitude is most likely to the equal to the maximum magnitude observed, like M1 method, if the historical seismology record is long compared to the recurrence of the interval of the M max. So if the seismicity rate is high. So basically I have the 200 years return period of earthquake, but I have the 1000 years data. So then I can go for this M observed as a magnitude, where it will be close to the M max. Okay. But this was most of the region in the world, this kind of scenario is not exist. So using of that is always one has to be very cautious. Second, so it provide lower bound of M max, whereas the M max estimation from incremental method is inconsistent. So you can also estimate a incremental method where you can add some value to the M observed value. Okay, that is a method 2. So according to Risk Engineering Limited 1998, the Bedinis, okay, so et al 1994, an increment of 0.5 to the observed magnitude for the site having B value of so much. So this 0.5 number is actually random. So some people even take a 0.3, some people take a 1, 0.7, so depends upon that. So there is no consistency among this one, and there is no reason, because if you see this minus 0.1 to this one, it's mostly most of the region you will get. That depends upon the your number of minor and major earthquakes. When we are talking about the recurrence relation, I will explain how the B values are varies there. So the mark, okay, he said that if you know the length of the fault, okay, then you assume that in the length 1/3 to 2/3 is going to rupture. So if I have the 100 kilometer fault length, I will assume that a 30 kilometer to 50 kilometer it is going to rupture. Since I know the rupture length, okay, subsurface rupture length, I can get a empirical equation which I discussed in the first slide. So then I can get a max. So that kind of method was suggested by the Mark. Okay, so that method is called as a Mark method. Okay, so the NPTEL, okay, so you proposed max event that would recur 1000 years region can be predicted by extrapolating the magnitude frequency graph of the steady region. So you can prepare a magnitude frequency graph, okay, then you extrapolate to the x axis. The magnitude frequency graph is basically this is the your m, this is your frequency. So you will be like this. So they extrapolate this like this and take this value as a your m max. So that is the magnitude frequency class which is proposed by the NPTEL 1981. So the max value computed extrapolation method is actually consistent with the size of the steady area, whereas inconsistent with the recurrence interval of the large earthquake. So the Wheeler 2009, so they studied detailed different max approach, okay, for the nuclear power plant design in US, and they taken a different approach and commented by doing the analysis. So that is what we are discussing right now, whatever points he has commented. The maximum magnitude can be also evaluated from the historic data by taking a arithmetic mean of the large earthquakes having the magnitude 7 and above reported in the seismic steady area. Okay. So the Wheeler was also suggested extrapolation can be done like this, arithmetic mean kind of. So the estimated seismic rate could be considered as a valid indicator of max, but failure sigma the instrumental seismicity suggests that validity of seismic rate is restricted approximately to the magnitude of 7 and above. So beyond that there is a issue with estimating that. So the extrapolation method and estimating should be used with cautious. That is what Wheeler says. So you can browse in the Google Wheeler 2009. What about he talks about the different max extrapolation and methods and all, if you want to do research on this area. So Gini and Aki proposed a inverse relation between the Quada wave. So the Quada wave means basically after the S wave you get a surface wave. No? Those waves are called as a Quada wave. So will helpful to hazard assessment in the region. The active region, the relative activity, okay, of the tectonic have the low Q0, whereas the most continental area higher Q0. For the stable continent region, the SCR, the earthquakes large enough to be taken as a max of the Q0. So that is what this was actually suggested by the Jenny and Aki. So this was having the different Q value, depends on that you can take this one, but there is a issue with the what type of seismic tectonic region. Okay, so like active region, continental region and stable continent region, you will have the different Q0. So Q0 based approach may not be again universally adopted. So then another approach we are using the strain energy approach. So what they did actually, Marco Polos and Burden, okay, so then Baylis and Burden have proposed an analytical method for maximum magnitude estimation of the region by using the strain energy released in the region. So the three magnitude have been defined which corresponds to the most probable annual maximum earthquake which depends upon the Gutenberg-Richter relation equal to AB, that is called as a ME1, and magnitude resembles the mean annual rate of energy released, that is ME2, the analytical upper bound of the earthquake magnitude which is called as a ME3. So in this what they do, they estimate a strain from the different earthquake in the region. Then they do the cumulation of the strain. So this is the strain. So when you are talking about actually when you talk about the magnitude size, we also discussed about the energy, strain energy versus the magnitude empirical correlation. No? So those kind of correlation which is reliable and applicable to your region you should take and estimate each year whatever magnitude happened, how much strain it's happened. Then you try to plot the year wise the data. Okay. So, then you will find a trend like this. Okay. This is the cumulative strain energy released in the particular region, which you obtained from the seismic steady area data. You already collected a data, no? From there you will get all the independent events after declustering the data and estimate a strain energy and plot like this. So, after plotting this, you plot a lower, upper and then the medium portion of the graph. Okay. The slope, okay, for example, so you can see the E2. So, the E2 is actually the median slope is the E2 energy that is corresponding to it. So, then the E1 is actually where you can see where it is hitting here, no? Then where it is hitting in the upper bound, you can see that this point and then this point and project what is the E max. So, this E max you can convert it into the magnitude, because you can estimate energy from the magnitude, again from magnitude to energy. Okay. Earlier you are estimated the magnitude to energy and used to cumulatively. So, now you are estimating the energy to magnitude. That magnitude will be unique for the different seismic steady area. Okay. That value will be taken as a M max value. This is the typical plot which shows how it is by taken. So, the another method is actually the Kitchko and Singh method. The Kitchko and Singh 2011 proposed a several procedure for statistical estimation of the M max based on the seismic data of particular region. Okay. So, these methods can be applied when no information about the nature of earthquake magnitude distribution available, when the earthquake catalog is incomplete. Okay. So, this is basically a statistical based approach. Even a incomplete data can be used here. Kitchko Singh proposed 12 procedure for the determination of the M max. So, this estimation of M max magnitude I have divided 3 category, parametric and non-parametric, fit to the cumulative density function of the earthquake magnitude. So, these are the 3 category they have done, and each category there is a sub estimation, depends upon the different composition and statistical model what they use. Okay. So, these methods so depends upon the time interval, number of earthquake occurred having the magnitude greater than or equal to the threshold complete of the specific steady area. So, this methodology assumes that magnitudes are independent, identical distribution, random values with the probability density function, the cumulative distribution of the function. So, this method basically you can see here. So, we have given this method, you can see the serial number. So, the parametric approach, the each method, the observation on that. Okay. So, you can see it is very straightforward method, does not require extensive calculation, but fails to provide estimate having the smaller mean square error. So, if you visit my paper on M max estimation, you can find more discussion about the all this method. So, the Kitchko released the computer program, okay, where it can be run in the MATLAB or any computer exe file, where you can get all the statistical method coded, where you can feed your data and get M max. So, the mathematical explanation also given in the computer program. So, if you are going to do research on M max estimation, you need to go through under the, otherwise this is the statistical method, depends upon the different statistical approach and data, you will get different M max. That message taken from here will be sufficient. So, this existing method whatever we discussed so far, okay, so are to be based on the frequency magnitude distribution and seismic data and observed magnitude. So, all this method whatever we discussed 7 method, you can see that is the function of existing data or frequency magnitude or observed magnitude. Okay, even a statistical method or any other method. These methods are suitable for the regions having the long historical and seismicity record. Seismicity rate is very high. These methods can be used. So, the M3 is consistent with the size of steady area, where whereas inconsistent with the recurrence interval of the large earthquake. Okay, the M3 method what we quoted there. So, the magnitude, maximum magnitude determined from the M4 is too high as far as low as the seismicity region concerned, because assuming the 50% and 1/3 of the data will be by mark, M4 method is more unrealistic. Okay. M6 assume that magnitude are independent, identically distributed random values with the probability density function and cumulative distribute function. Moreover, many of these areas are inconsistent with the selection of the seismic steady area. Most of this method does not account the regional rupture taking place in the particular region. So, in order to account that, okay, we come up with the new idea called regional rupture character. Okay. So, what is the regional rupture character? As we have seen that the rupture occurring at a particular location is the function of your shear wave velocity or stiffness of the particular rock. Okay, that is what we models. Okay, shear modulus or shear wave velocity, that, and then the density and the type of the rock. Okay, at the particular location. So, the crust rock at rupture place, the controlling, these are all the parameters which controls. So, the changes in these parameters will also result in the changes in the your rupture phenomena. Some places, if the rock is very weak, it may rupture larger for the same magnitude. Some place where rock is very strong, it will rupture less for the same magnitude. Okay. So, if the rock is uniform in the region, then the nature of rupture will be also uniform in the throughout seismic steady area, which means that the average rupture dimension with respect to the total dimension will be also similar. So, if you have the seismic steady area which has a uniform rock deposit from the crustal rock deposit or any geological formation, that means your rupture phenomena also similar in that region. So, by taking this as a consideration, one can establish what is the regional rupture character. Okay. So, how to establish that? So, you take a length of the fault, okay, and take a damaging earthquake. Damaging earthquake means a earthquake which can rupture a fault, okay, the 4.5 and above magnitude, and try to estimate what is the subsurface rupture length, okay, using the well known correlation between the subsurface length and magnitude. Okay. That RLD you can take at a different fault and different earthquake occurred in the your seismic steady area. If your geology of the steady area is same. If geology of the steady area has a 2-3 division, then only adapt to the similar geology of this. Okay. Once you take that, then try to normalize that value with the length of the fault. Then we plotted that with the again the length rupture length ratio versus the length of the fault. We got a unique trend. That trend we call it as a regional rupture character. Okay. So, let us see, before going to estimation of that, let us see what are the empirical equations are available for RLD versus magnitude. So, this was actually published by the Wells and Coppersmith in 1991, even it was also recently updated, but the update was not so much, actually more or less the same. You can see that the moment magnitude and the any other magnitude well related with the fault rupture length and fault rupture area, again is the function of different fault type, okay, different tectonic settings. Okay. So, here you can see that subsurface rupture length, so the surface rupture length. Okay. Subsurface rupture length means the ratio between the ruptured below ground and the surface, that also follow a unique trend which is differentiable with the different fault type. Again, this is for the another region where you can see the subsurface rupture length and rupture length. So, based on this kind of systematic analysis of the entire global data, E has given a relation between the M versus subsurface rupture length and surface rupture length. Okay. So, the subsurface rupture length is which is the one which is controlled by the fault, okay, and rock in the region. So, we take that as a basis. So, the equation given for the magnitude versus subsurface relation, a particular fault type depends upon the your fault orientation or fault type in the region, are applicable to all the fault you can take. Okay. So, that equations you can take it as this one, like subsurface rupture length, moment magnitude, a different fault type, and this is the relation you can take. So, after taking that relation, you can estimate for the damaging earthquake, like earthquake which has a magnitude of above 4.5 and above, you can estimate the subsurface rupture length using this kind of empirical relation. So, this is a typical relation, but you can use the recent updated equation also, no issue. So, you can get that. So, as I told you that you estimate first RLD, okay, divide the RLD is the subsurface rupture length, divide by the total length of the fault, and then plot again a total length. Then we notice that these are all the data what we got it from this one. When you fit a trend, it follows a unique trend. This trend is called as a regional rupture character. Okay. So, this trend is same for a particular region as long as there is no rock changes are occurring. Okay. So, this concept, once you establish that, now you know that what is the trend, you can decide what is the rupture length percentage you can take. Okay. Then that you can again convert into the magnitude, that magnitude will be taken as a maximum magnitude. Okay. So, that procedure and the explanation about that I am going to discuss further in the class. So, this procedure is streamlined like that, it has a 5 major step. So, determine the maximum magnitude observed on each fault, okay, which is damaging earthquake, and then the total length of the fault you can take from the map. So, estimate RLD, okay, using the Wilson-Coppersmith relation, like this is the inverse of the relation what is given in the table, and determine the segment of PFR based on the different TFL basin observed in the worst case. So, here you can mark based on this, you can mark that, okay, up to 100 this is the this one, up to 100 to this one, this segmenting you should do carefully by looking at the this line and the maximum and the minimum, okay, that you can do. So, then after that based on the segment you can fix what is the ratio, okay, this ratio you can take it for your analysis, percentage of the fault rupture you can take, then use that again in convert into the magnitude using the same equation here. So, here that plus or minus has been taken as a upper side. So, the equation comes as a only one, this one there is no standard deviation. So, this process involves a 5 step which is very simple. How, let us see how this concept is applicable for different part of India, how it represent a the overcome a limitation in the previous method. Okay, that is what we are going to discuss further. As I told you that the present practicing whatever the method 7 method we discussed, it has a problem whenever there is a change in the data, your Mmax will be changing. Okay, change in the Mmax occurs because of the change in the seismic steady area, which changes your data, that also result in the change in the Mmax. So, we need a method which does not affected by the this kind of seismic steady area change and then the data change. So, the rupture based method will actually work like that. So, in order to demonstrate that, we have taken a 2 region, one is that a Patna, the another one is basically a Kalpakkam. So, where the southern India and north India stable continent, interslab and intraslab. Okay. So, both are taken. So, we have taken this is a steady area, this is a seismic steady area. So, we have taken a 3 radius of seismic steady area. So, 150 kilometer, 300 kilometer and 500 kilometer radius. So, let us see the data in the 5. So, the 150 kilometer number of events is actually 72 and 300 is see how much increased, 500 see how much. Maximum observed magnitude, minimum observed magnitude 2.4, 1.7, 1.7, maximum observed magnitude 5.8, 6.5 and 7. Why you need this? Because you, as I said that Mmax method, one of them is maximum observed plus maximum observed by increment. There are 2 methods depends on that. So, that is why you have to take. So, the number of event less than 3, so you can note down, number of event more than 3 you can say. So, this all will tally actually when you do that. So, the number of seismic sources fault associated with the earthquake and the AB parameters which we will be discussing in the next how to estimate AB parameter. So, that also we have taken because the statistical method basically looks at the AB parameter of the your data. So, the regional rupture character we try to establish for the same study area by dividing data into that and estimating the RLD percentage and plotted. You can see that irrespective of the radius, okay, you get all the line similar. Okay, the trend is similar irrespective of the radius. So, which will help you to basically to arrive your segment also similar. Okay, so I can arrive up to this, then maybe this. Okay, so then maybe this like this. So, you can also see the unusual earthquakes. So, which you can also consider away from the trend, but it has to be noted when you are assuming your RLD percentage. Okay. So, that flexibility also gives in this method. So similar map has been done for the again a Kalpakkam. So they again 150 radius, 300 and 500 radius. So similarly all map seismotectonic map has been prepared and then try to the, so establish a segment, you can see here segment 1, segment 2, segment 3, you can see the rupture character. So here you can see that there actually the Patna has a geologically different region, because if you see the Himalayan side and south and west, since we consider all of them, the gap between these are slightly larger. Okay, when you go higher radius, the geology composition come into picture, which result in the different to this one. So that means we have to divide that as a different geological formation and establish this one. But in Chennai, it's the same geology, because it's a southern granular terrain. You can see that a very closer lines. Okay, there is no even a small deviation in this. Okay, so you can see the 150 in blue color, 300 in the red, and then the green is actually 500 radius and the trend. So you can get a 3 segment. So once you arrive this segment, okay, so this is basically for the again Patna. So you can decide what is the average value, maximum value, then you can decide, it depends upon the structures, what value you want to take for the safer side and convert into the max. So that value we are going to discuss further. So it can be observed from the percentage of the total fault rupture, short fault length having the more rupture than compared to the long fault length. Okay, the showing the decrease in the trend with increasing the fault length. Okay, the RLD actually is a function of the length of the fault, which is again controlled by the geology, rock properties in the region. Indicates that most of the damaging earthquake in the region somewhat follow a some trend which is unique. So the trend of PFR, okay, fault rupture ratio, okay, does not vary with the seismic steady area, also fits better due to increase in the seismic steady area radius. You can see the maximum, minimum, average. So this value, okay, you can decide what is the proposed rupture length you want to take, or percentage of the rupture length you want to take. So as I know that the maximum is 25, okay, so I want to go for the worst scenario where I will be taking larger. Okay, so then the 22 larger and this one. So if I want to go for the little like the worst scenario for the nuclear power plant dam site kind of things, where the worst earthquake should not even affect those structures. So if you want to go for the regular building, you can close to the maximum, do not need to have the so much variation with the maximum value. For example, here the factor which varies with the maximum value. So this also you can take. So this factor you can decide, depends upon the importance of the structures. So the more important, the more factor should be given. Less important, factor should be reduced. Okay, that is what you can do. So this is the way we can estimate. So let us see how the max from different approaches are required. So since all other method are only analytical method, this is the graphical method. So the energy based graph has been prepared for the both the region. So this is the energy based graph for 150 radius. You can see the ME1, ME2, ME3 for the 150 radius. Again for the you see for 300. So these values are changing now. Again for the 500, you can see how the changes. So the even energy based method also reflect a seismic steady area, this one, but RLD doesn't do that. Let's see how the calculations are there. So this is similarly for the Patna, where we have shown only one graph. So after doing this, so this is the different source, okay, then the total fault length, okay, RLD rupture estimated, and then the converted that RLD assumed value as a maximum magnitude with individual fault. Here you also have the advantage that each fault you can get a max. You can see that these max are completely different from your observed max, you can see. Okay. So these max are consistent with respect to the length of the fault. This is nowhere related to the length of the fault, that also you can get. And again the radius. Okay. So when you consider lower radius, you will get only the few sources into the band. Okay. So this we will see in detail how it affect this one. So the similar kind of like the Kitchko and Selwell method we have used. Okay. So to get a M minimum and then this AB parameters and thereby 12 M max estimation method. So that method also given here, you can see. So this table, okay, so gives a very detailed analysis of your M max estimation. So this side basically gives a M max estimated method, like MM1 means method 1, M max by method 1, M max by method 2, so M max by method 3, like 8th method is proposed by myself and all other method were existing one. So MM1, okay, so where the observed magnitude, so 5.9 when I consider the 150 kilometer, and 5.9 again 300 kilometer, and 6.3 when I go for the larger seismic steady area. You can see this 6.3 and 5.9, you know this is 6.3 is 40 times larger than the 5.9, oh sorry, 4 times larger than the 5.9. Okay, so even though the variation is 0.4, but it is 4 times larger than the 5.9 as it is in the log scale. So the M2 method, increment method, so it depends upon the AB value, even though the recommended. I have taken here 2 cases where I added 0.5 and I added a 0.1. You can see the M max, so much difference. Here you can see this one similar, but here you can see as the observed magnitude changes, your M max by increment method also changes. So the extrapolation method graph, this is the one, this is the one, and this is the one. Okay, so you can see there is a consistency increasing in the M max with increase in the seismic steady area. So the quad wave method, so this gives almost the same value because the quad wave portion remains similar. The mark method 8.1, 8.1 and 8.1 because the length, this was actually we are given the highest magnitude on each method. The strain energy method you can see here, it is around 4. So here the 4 to 5.25, here 4.4 to 6.5. The 6.5 is can be taken as a the M3, that is what suggested. The Kitchko method you can see a different method, M1, M5, M6 give the similar value in 12 method. So then the M2 and M3 not applicable, M7 and M8, M9. So the within the Kitchko method I said there are different methods are there, 12 method. So you can see the difference, okay, how the each region the values are taken 6.2, 6 and 6.49 a particular. So like that is 6.73, okay, so the so M6 no 6, so then here the again M6 where 6.4. So we have did a careful analysis and try to compare these values. Let us see what the regional rupture character gives. The proposed method, you can see that the M max varies from 5.8 to 6.9 for the total derived from so much rupture length. It varies from 5.8 to 6.7 with the so much. It varied from so much to so much. You can see that here the upper magnitude remains same, okay, and each fault you will get a M max. Okay, but the rest of the method you will take each fault means sometime if there is no earthquake recorded in the fault, okay, only the 1 magnitude, 2 magnitude reported, you consider that that fault does not have the M max at all. That risk is there in the existing method, but new method it consider all the fault. So you can see here the graphical representation of the M max variation. So this is basically a different method in the y axis, the x axis you can see M1, M2, M3, M4, M5, M7 and M8 method. So this is the magnitude which is estimated, okay. This line indicates a reported maximum magnitude in the particular seismic steady area, okay. So here the line upper and lower bound gives a variation within the particular method. So you can see that the most of the method up to M7 method there is a huge difference, the upper and lower bound you can see here. As your seismic steady area changes, your M max also fluctuating, you can see here. Your M max also fluctuating and that is also on all the method, okay. So you can see here. So some of the method even give a very different value when you change your seismic steady area. So if the same thing if come back to the newly proposed rupture based method, you can say irrespective of the seismic steady area, you get same M max, the variation also similar, not like other methods. So this is the beauty of the regional rupture character approach on M max estimation. So this particular work was already published in the Journal of Seismology. Now people start using this one, this kind of approach for estimating the M max at a particular region. So I suggest that instead of adding a 0.5 or random value, it is always better to take this kind of universally acceptable method, because it does not depends upon your seismic steady area at all. It only depends upon your geology classification at a particular place, how geology is complex on that particular place. So recently also we have validated this method with different papers in the KRS dam. Those who are interested to more about this, you please visit those papers and read those papers and try to understand. So this is basically a particular steady area. So then we further went to the other, this one, there also you can see this is I think for the Patna, earlier one for the Kalpakkam. You can see the how much difference. See, so these differences are negligible, okay, in the difference are negligible in the this newly proposed method, which need to be considered as one of the best way to estimate a max. Okay. So this has been published in the Journal of Seismology, as I said you that. So I believe that this kind of approach will give you the unique max at a particular region. Okay. If you want to consider entire seismic steady area as a single region, and or you also get a individual fault length based max, which is also possible. That also does not change irrespective. But other approaches, when you change a seismic steady area, your max value keep changing. That is not the issue with the newly proposed method. So by looking at what is the importance of the max and how the different way you can estimate, and I also discussed the method which unbiased, because all other methods as a bias depends upon your seismic steady area. So if max method proposed by regional rupture character, if you use, you no need to worry about your seismic steady area and all. But still you have to consider the seismic steady area as a very important, because your recurrence relation, okay, is the function of how many earthquake data you have, like magnitude frequency plot. Okay. So the magnitude recurrence relation is the function of how much data you have in the particular region. So that way the seismic steady area and plays a very important role, contributes to the max as well as the contribute to the recurrence relation. So we will discuss about the recurrence relation further in the next class. Okay. So about the recurrence relation, so how to estimate, how it's controlled by this one. So right now we have seen that the selection of seismic steady area and associated effect on the max, and I suggest that the regional based max estimation will be the more reliable based on my research. So if you want to do other approach also, you are welcome. You can take both the method and compositely you can mix and estimate a hazard, which we will discuss when you are talking about the hazard analysis at a particular place. So this is about the max estimation, which is also one of the important step in the seismic hazard analysis. So with this we will close this class. So thank you very much for watching this video. So next class we will be talking about the recurrence relation, okay, development for a particular place. So thank you very much for watching this video. So we will meet you in the next class.